That makes for a good video. I'll make sure I come closer so we can hear all these comments you make. Hear your non-stop comments. This first one here is essentially the definition we have, the original definition, right? The derivative at a point is we're going to start at some value a and then add a little tiny bit, and then the slope between those points is that divided by h, that difference divided by h, and then the slope of the tangent line is when you push the 2 points right together, taking the limit. The alternate way we can find this definition is this second thing here. Instead of calling the 2 points, instead of calling them a and a plus h, you could say that this is some point a here and this is x. So instead of saying the distance in between them is h and I'm going to make that approach 0, you can say I have 2 points here and I'm going to move this one closer and closer. Okay, as in you take this one and make it approach the a value there. So the derivative of this is as x approaches a, not as h approaches 0. It's the same thing, it's just labeling it different and setting it up differently. Okay, having two different values there, and it actually looks more like the slope formula than you're used to, and maybe this would be more intuitive as a way to set it up. You have two different values. If you want to know the slope of the tangent, you just take this part and move it closer and closer to the other one. The reason that we have this alternate definition is sometimes, like this original definition works well if you can make the algebra work, right? Like in this one, if you look back to this, all our nice algebraic work here, when you expand this thing and then subtract x cubed, eventually this cancels out. For any polynomial, it's going to work out that way. And the reason that that helps is because then now everything up here has an h, and you can divide by h, and then you can sub in the 0. Whereas for some other kinds of functions that aren't polynomials, that's not going to work. This one happens to be one that this y equals root x happens to be one that's not going to work this same way here. If you use this alternate definition, you can simplify it using this. So if we say that the derivative here, we're going to say f prime of x, or d dx of f of x, or whatever you want to call it, that derivative is equal to limit as x approaches a of, we need f of x minus f of a over x minus a. So filling in the specific function, you got root x minus root a. X is the point that we're moving. A is the point we want the derivative at that point. Over x minus a. Now that seems like maybe you can't simplify it, but what can you do there? Can I sort of start crossing things out like this and say root a and a can cancel to root a? Can I? Of course not. What you can do is you can actually factor this. When you first learn to factor, you don't think of factoring that into using roots, but you can factor that. Let's create some space here. You could make this equal to this on top, okay, that factor, but on the bottom, x minus a, you could make root x plus root a times root x minus root a, just like any other factoring thing. I mean, multiply that out and you see it works, right? Because the middle term is going to cancel. It's the same as how you can make, a squared minus b squared into a plus b, a minus b, right? Okay, just factoring it like that. Now you can simplify it by canceling out that whole factor. And maybe it would help to look back at why we couldn't have just worked out what this limit was right off the bat. Why couldn't we work out what this limit was right off the bat? What would we have on the bottom here? Yeah, if x is approaching a, to try and evaluate it, I mean, the first thing you should try and do is just evaluate it as is. You put in x for a, or a for x. If you replace that with a, you got a minus a on the bottom, and it's not going to work, right? But now that you do this, if x is approaching a, then x is becoming a here. So to evaluate this, 1 over root a plus root a, or in other words, 1 over 2 root a. That's the derivative of that function. You could confirm it on a graph for yourself just by checking the values at any particular point. If you wanted to. If you graph that original square root of x, this time maybe we'll use a calculator instead, because that's the technology you have in front of you. Okay, so you put in, we want to graph that original function, square root x. We'll do, start with zoom decimal here maybe, just so the numbers are nice on the graph. Maybe we'll adjust this so that we can see just the part we want here. Negative 0.7 to, what did I do there, 8.7. If you want the slope at any point here, let's calculate the slope since this is not as dynamic as the other one here. Actually, we could graph the derivative here as well. We'll make this one a thick line. It's the original function. And the derivative at any point is 1 over 2 times the square root of the a value. So the derivative is 1 divided by 2 root x. Right? Anywhere I sub in a certain value here, that's the derivative. So if you graph this, there's the original function. There's the derivative. The y values of this bottom function, the y values, the function values represent the slope up here. So calculate the slope anywhere on this curve up above. Okay, we'll do it at one point. We'll do it at 4. How about that? Because it'll be a nice number. What's the slope, or what's the value of the original function? The original function is y equals square root x. So obviously the original value here is the value at 4 is 2, right? What's the slope at that point supposed to be here? What's the slope going to be? What does this say the slope's going to be? This 1 over 2 root a? 1 over 2 times the value? It's supposed to be, well, it's 1 over 2. Let me draw this on here for you. Draw tangent. I think I have to go on this. Okay, it's not really easy to see, but this is the slope of that line. When x is 4, I did it to the wrong curve. Let me cancel that. Yeah, why didn't you say that? Okay, let's try that again. Draw number. Don't put it on the derivative. We want it on here, right? You want the slope of that curve? And it says, remember, you can't trust it past several decimals, but a quarter, right? Because you put 1 in, you put the y value in there. You guys are obviously ahead of me here on this anyway, so. The slope of that curve is this, the y value here, right? The slope of that tangent up there was a quarter. The y value here is a quarter. As you go to the right here, what's going to happen with the slope of this curve? Yeah, it's decreasing, and then this makes sense, right? This is decreasing here. Over here, the slope is steeper. That's why this is higher. This is going to go up to infinity there, and it's actually going to be undefined at 0 because this is completely vertical at 0. Anyways, we're going to the connecting the graphs is tougher, I would say, but you can work with that as we work through this unit.